Okay, so what does all this average rate of change in secant line business have to do with this other concept called a limit? Well, it turns out that limits come up in the theory of derivatives, which is where we really need them, at least for calculus. They're also useful in general. To get an idea of what's going on here, let's look at this example. So, suppose you have something similar to before. So in this example, we have a car traveling in a straight line, just like before, and its position is given by, we're going to just keep it simple and just have s of t be t squared. And then the question we want to ask is, what is the car's speed or velocity at the moment that t is equal to 2 hours? So we have to be a little careful here, because if you really think hard about it, it may be not quite so clear how you calculate the speed of an object at a single moment in time, right? Whenever we, typically calculate something's speed, we need to see like how far it went over a specific time interval, right? We need to see like how far it went in 1 hour, or how far it went in 1 minute, or how far it went in 1 second. But if you just have a single moment in time, how do you measure how far something went? And this is kind of where calculus starts to get in, because we have to say what we mean by calculating the car's speed at a specific moment in time. Otherwise, it's not so clear. So what we do, and we'll get to the formal definition later, is here's the idea. The answer here is we approximate the car's speed over very short time intervals that contain this 2 hours mark. And as we if we did this for shorter and shorter intervals, so as the intervals become shorter and shorter, the average rate of change over these intervals turns into the instantaneous rate of change. Let me write that out. Which is measuring the speed or velocity at a single moment in time. Whereas if you think about it, the average rate of change is measuring kind of the speed over an interval of time on average. So it's saying we can define the speed at a moment as being what happens on average over shorter and shorter time intervals, including our 2 hours. So what we do is we say, well, let's pick some intervals that include 2 that are very short. So first thing we might do is we might calculate the average rate of change of s of t over the time interval between. So you could do many things. You could do like minus 1.9 to 2.1. That includes 2. But it turns out that a nice way to do it that kind of makes everything uniform is to use 2 as one of the endpoints of the interval. And that's kind of the convention we're going to stick to. You don't have to, but it'll turn out that that's kind of baked into our definition of the derivative, so we might as well get used to it. And this is going to be equal to s at the endpoint minus the position at the beginning over the difference, which is just 0.1. Then we have to plug this in, so this would be 2.1 squared minus 2 squared over 0.1. So you throw that into a calculator, what do you get? You get 4.1 miles per hour. So this car is not going very fast. So that's still an average rate of change if we want to, but the idea is that it should be close to the instantaneous rate of change because, you know, we're taking a very short time interval. We're taking, you know, it's only 1/10 of an hour has elapsed here. And so you would expect that over a shorter time period, the speed of the car varied less, so it would be closer to what its actual speed would be at the moment. But 1/10 of an hour probably isn't that exact, so maybe we try to make it even more exact and we compute the average rate of change of s of t over the interval. We're going to make it shorter, so maybe we go 2 to 2.01. So now this is 1/100th of an hour is the time elapsed here. And we do the same formula, so it'll be s of 2.01 now. Yes, s of 2 over 0.01. So if you throw that all into a calculator, you get 4.01. So it looks like it's getting closer to 4, and this has the same units, miles per hour. And to make sure it's really headed towards 4, we can maybe do one more. We could repeat this, so I'll just do this quickly. Where now our time elapsed is 1/1000th of an hour. And so what we see is that over in shorter and shorter time intervals, the average speed is getting closer and closer to 4. So we might guess that the speed at t equals 2 is, you know, we can't be sure. Later we'll have a way to make sure that we're being exact. That's approximately about 4. You know, it's got to be pretty close to 4 because it's got to be pretty close to 4.001. Okay. And so if you look at what we're doing here is, so what's the pattern that's going on here? So the pattern is we're calculating average rate of change over an interval where it goes from 2 to 2 plus a little bit. And that little bit I'm just going to call h. Like h could be some really small number. Okay. And if we look at it like this, well, if we do a little simplification in the denominator, we get just an h. And the question we're trying to answer is, what happens as h gets smaller and smaller? So a lot of times what we say is what happens as h goes to 0, as it approaches 0, as it gets really, really small. And so you might be tempted to ask, like, because we're really interested in, like, what happens when h actually gets to 0? But if you think about this, this is not defined. When h equals 0, which is what we are interested in. So we have this formula, we have this, you can think of this as being a function, this fraction is being a function of h. Right, I can plug different h values in and I'll get different values out. Right, up here we plugged in like h was 0.1, then 0.01 and then 0.001, and we got these different numbers out, right? So this whole thing together is a function of h. And we're really interested in what happens when h is 0, but the formula here doesn't tell us what happens when h is 0. And so this is where the idea of a limit comes in. Okay, so let me give you a preview of our next video. The limit as h goes to 0 of this quantity is exactly so we're going to talk about this idea of a limit, and what that's going to tell us is we'll have something called the limit as h goes to 0 of this fraction, and what that ends up being is exactly the thing we're interested in, is what the value of this thing should be in some sense. When h equals 0. So somehow this formula here contains enough information to tell us what the value should be at 0, and that's what the limit will tell us.